Let's have a look at another example of how we can use complex contours to help us calculate tricky real-valued integrals. And the integral in our case here will be an integral from 0 to infinity of cosine lambda x divided by 1 plus x squared dx. And lambda happens to be a number with a positive outlook on life, so it's bigger than 0. Okay, in order to use our machinery of residue calculus, we basically need two ingredients. We first of all need to figure out what our function f of z will be. That will help us to calculate the relevant real-valued integral. And we also need to have a contour. So these are the two ingredients that we need in any problem like this. So let's first have a look at the function f of z we're going to use. An obvious choice would be to just replace x by z everywhere, giving us cosine lambda z divided by 1 plus z squared. That's fine, that would work, but as we will see later on, this particular choice will actually cause us to do a lot more extra work, and we don't like to do extra work in case it can be avoided. So this is why we're going to use a slightly more convoluted choice of f of z, which will help to save us a lot of trouble in the long run. We're going to use f of z is exponential j lambda z divided by 1 plus z squared. How are we going to get from f of z back to our real-valued integral over here? Well, we're going to evaluate this function f of z on the real axis. So on the real axis, this just becomes again exponential j lambda x divided by 1 plus x squared. And then if we have our result and we take the real part of the expression, then our friend Euler tells us that this is going to be equal to cosine lambda x divided by 1 plus x squared, which is indeed what we're interested in. So this is the choice of f of z that we're going to make. And later on you will see why this is much more clever than this particular choice over here. Good, so this is this part taken care of. What about the contour? For the contour, we need to look very carefully at the limits here. So here we have a limit from 0 to infinity. So don't be tempted, for example, to use the unit circle, because this is something that would be useful in case we had a limit from 0 to 2 pi. But here we're not dealing with that situation. We're dealing with something else. We're dealing with an integral over the positive real axis. So our contour should indeed contain something that has a relationship with the positive real axis over here. Our contour should also be a contour, obviously, which means we need to close it. And let's just for fun try and close it with a semicircle. It's always a good first estimate here when we try to construct a contour. So let's just try and see what happens if we use this contour over here. So we'll start out from a finite radius of our circle, but obviously the goal is to have r moving towards infinity, such that eventually the whole positive real axis will be part of our contour, which is indeed what we're interested in for our real-valued integral. But you might protest, well, okay, I have what I'm interested in over here, but there's many more things going on in these contours. We have also this contribution here and that contribution over there. What are we going to do with those? Well, later on, we're going to tackle that problem indeed separately. But for now on, let's just focus on calculating the value of a contour integral of a function f of z, which is given by this expression, over this particular contour over there. And then later on, we're going to break apart the different contributions such that we hopefully can learn something interesting about this part, which will tell us something about our real-valued integral. So what I suggest you do now is pause the video, try and figure out where we have poles inside our contour, and then calculate their residues. Let's have a look at the poles. We have 1 over 1 plus z squared here. So our two poles will be at j and at minus j, so j and minus j. Obviously, in the limits of r going towards infinity, this j will at some point be part of our interior of the contour, and we never need to worry about minus j. So the only pole we're interested in is the one at j. To calculate the residue at j, we're going to use the formula where we just take the numerator as it is. So this is exponential j lambda z. We take the derivative of the denominator, giving us 2z, and we fill in j. We fill in the value of the pole. This will give us exponential minus lambda divided by 2j. And if we take that expression and we multiply it by 2 pi j, then indeed we have everything we need. We have calculated the value of our integral. Let's now start thinking about the different contributions to that integral. So we have a contribution along the real axis here. So we have a contribution from minus r to r. And then along the real axis, we can write exponential j lambda x divided by 1 plus x squared dx, because we're on the real axis. And then we have a second contribution from that semicircle over here, and I'm too lazy to write the integrals. And the result of that contour integral is, again, 2 pi j times the value of the residue we calculated, exponential minus lambda divided by 2j. So this is just pi exponential minus lambda. Okay, let's first focus our attention on this particular term over here. So what will happen is we're going to take the limit of r going towards infinity. Can we say something about the contribution here from this particular term? Obviously, some sort of limiting theorem will come into play. Pause the video, think about this, and try and figure out what the contribution of this term will be. So there's two candidates here. There's the big limit theorem and Jordan's lemma. Both deal with circles where we have radii running off towards infinity. But in our particular case, we see that we have an integrand involving a complex exponential here. And that, of course, points towards Jordan's lemma. So let's have a look at the different conditions that need to be fulfilled for Jordan's lemma. First of all, we need to figure out that our contour is in the correct half plane. And then we need to calculate some sort of limit. And if both of these conditions are fulfilled, then indeed the contribution from Jordan's lemma here, from this particular semicircle, will vanish. So let's verify if these conditions are fulfilled. First thing we need to worry about is the so-called correct half plane. So for that, we need to figure out what the origin of our circle is. So the origin of our circle obviously is this point, the O here, the origin. That's going to be our value of A. And then we need to look at B, which is our exponent of the complex exponential. So B is going to be j lambda. And then remember, the next step in our construction is looking at A plus B complex conjugate. So this is giving us the point minus j lambda over here. Next step is drawing a line from here to here, then drawing a line perpendicular to that, and then looking across from that point A plus B complex conjugate. And that will give us the correct half plane, which is in our case the upper half plane, which is luckily where we decided to close the contour. So a contour in the upper half plane here means that the conditions for Jordan's lemma are fulfilled. Second thing we need to figure out is we need to calculate a limit at infinity and verify that that limit is equal to 0. So the limit of z going towards infinity, in our case of 1 plus z squared, that thing should be 0. Remember, for Jordan's lemma, we do not need an extra factor z minus a here, so don't confuse the big limit theorem with Jordan's lemma. This thing will be equal to 0 because the denominator always wins out. If you want to make this slightly more rigorous so that we can easily be convinced that this is true for all possible directions under which you choose to approach infinity, we just write this as 1 plus the modulus of z squared exponential 2j, the argument of z. And then because this thing with the complex exponential is always finite, it's very easy in this expression to see that regardless of the value of the argument of z, if the modulus goes towards infinity, that this thing will always vanish. So the two contributions are fulfilled. We can safely make use of Jordan's lemma and then decide that this thing vanishes. And now is a good time to revisit our choice of f of z, because had you chosen, for example, cosine lambda z as a function, then we would be in a little bit of trouble here, because we know that cosine of lambda z is exponential j lambda z plus exponential minus j lambda z divided by 2. And then you had two different complex exponentials with a different sign here. So this means that you would have to calculate two separate integrals. One integral only taking care of this particular term with a contour in the upper half plane, and then a second integral involving the second term here with a contour in the lower half plane. And that's of course a lot of extra work. So thanks to this trick of taking the real parts, we only need to worry about a single contour and a single f of z. So that's of course very useful. Good, so we've gotten rid of our C of R here. Let's now pause the video and try and figure out what happens in the end when we take the limit of R going towards infinity, and see if you can then finally calculate the integral from 0 to infinity of our particular integrand. So yeah, let's just write down again what's going on. If we take the limit of R going towards infinity, we have an integral from 0 towards infinity, exponential j lambda x divided by 1 plus x squared dx. And we've calculated that this is equal to pi exponential minus lambda. However, if we want to be really rigorous about it, what we need to add here is the principal value of the integral. Because have a look at our contour, what's happening. If we take the limit of R going towards infinity, this means that we will approach plus infinity and minus infinity in a symmetrical fashion. So we will not be in a situation where we take the limits towards plus infinity and minus infinity completely independently from each other. So therefore, what we really mean is the principal value of this integral. That's what we've calculated. And this thing is equal to pi exponential minus lambda. And now we're almost there. We need to take the promised real part of that integral. So then we have the principal value 0 minus infinity to plus infinity cosine lambda x divided by 1 plus x squared dx equal to pi exponential minus lambda. Finally, let's figure out what happens if we look at the integral from 0 to infinity rather than from minus infinity to plus infinity. But luckily, that's very easy to figure out because our integrand here is an even function. So cosine is even and x squared is also even. Because we're dealing with an even function, we can say that our desired integral that we wanted to calculate from 0 to infinity of cosine lambda x divided by 1 plus x squared dx is equal to pi over 2 exponential minus lambda. Okay, so there we have it. Another nice example of how the machinery of complex contour calculus and residue calculus can help us tackle finding the values of rather nasty looking real valued integrals.